So the easiest case is what we call quadratic optimization or quadratic programming. It is the minimization over the parameter space of J of S that is defined as a certain quadratic function of S. So how do you usually write down a quadratic function if the parameter is a high-dimensional quantity? So if S is a vector, what is a quadratic function of S? S squared, that's actually one type of quadratic function, right? Here, again, J is a scalar, and S is a vector. Is usually a lot higher dimensional. So S squared would work if S happens to be a one-dimensional vector, right? Okay, so another is S dot S or S transpose X if you write in matrix notations, right? So that's a quadratic function. What else could be a quadratic function?
Plus S.
Yeah, plus S. So it's actually true. If you have a quadratic function, the quadratic function plus any linear function is still a quadratic function, right? Okay? But can you think of any other quadratic function that is in a different form than this? Let's just imagine, for example, let's make an example. Maybe that helps a little bit. S is equal to S1 and S2, so it's a two-dimensional vector. Can you think of a form J that is just written in terms of S1 and S2 that is quadratic?
S1, S2.
Yeah, S1 times S2 is also quadratic, right? To easily see that, if I define J as S1 plus S2 squared, that's obviously a quadratic form, right? It's a linear combination of the two parameters squared. It's quadratic. That will have a S1 squared, S2 squared, and 2S1, S2. So this is actually a quadratic term. It's one component of the vector times another component of the vector. It's quadratic. Okay? So to make it more general, how should we frame a quadratic function if S is a vector?
Si, Sj.
So here the proposal is Si times Sj, right? That's one of the terms that could be any combination of I and j, could be a component in the quadratic form, right? And also, I can have the SI-SJ term, I cannot have SI-SJ term, and I can also have any multiple of SI-SJ term, right? So how about multiplying this SI-SJ term with the Aij and sum them up, right? So that's a typical quadratic term. Actually, that covers all possibilities of quadratic terms we could have. And can anybody write this down into a more compact form using linear algebra?
S vector times the matrix A times the vector S.
Yes. So if I write down S like this in a column vector form, this is actually equal to S transpose times A times S, where A is equal to the matrix of Aij. So that is a general way to write a quadratic function in the vector space. So here the only modification I need to do is to insert a matrix A in between S transpose and S. How about the linear term? what is the most general linear term? A scalar linear function. Yeah.
Vector B of coefficients dotted with S.
Yeah, a vector B of coefficients dot with S or B transpose S, right? If S and B are both column vectors. So one thing I hope I can get to a little bit more familiar is how to express ideas and mathematics in terms of matrices. Because computers, when we think about how to solve problems with computers are actually not very good with general mathematics, but it is particularly good with linear algebra, with dealing with matrices. And that's just an accumulation of many different algorithms since the beginning of computational mathematics. We have a huge library of algorithms that deals with linear algebra. So if you can turn your problem into a linear algebra problem represented in terms of matrix and vectors, there is a very good chance you can efficiently solve it with computers. All right, so here, it's a good news that we can represent a quadratic optimization problem in matrices and vectors. And that's actually very good news because there is a good chance computers can solve it very efficiently. All right, so how do we solve it? Actually, where have we seen this type of problems, minimization of such a functions, in this very course? Finite elements, exactly. So in finite elements, the objective function usually happens to be the energy of a structure or a heat transfer type of problem, right? And the parameter S is actually the deformation or the temperature distribution after you discretize it using something like a nodal basis. So we have already looked at how to solve these kind of problems, but today we're going to do it again.